Today. We're delighted that Professor Robert Houze was able to join us this afternoon, and we're presenting the Symons Gold Medal Award at our award ceremony later this afternoon, but Robert's here to give us the Symons Gold Medal Lecture. Professor Robert Houze has revolutionised the manner in which meteorologists and climatologists think about atmospheric convection. He received a Bachelor of Science in Meteorology from Texas A&M University in 1967. He received his Master's and PhD degrees from Massachusetts Institute of Technology, and he joined the faculty of the Department of Atmospheric Sciences at the University of Washington in 1972. During his tenure at the University of Washington, he's graduated 20 PhD students and hosted 10 postdoctoral fellows. His careful and thoughtful mentoring has led many of his group to attain positions of importance around the world. He's made the university the centroid of cloud physics in the United States. So I'm delighted that Robert is here today to give us the Symons Gold Medal Lecture on the many ways that mountains affect precipitation.
Thank you, Liz. It's really a great honor to be here today. It's hard for me to overemphasize that. It's just a wonderful feeling. I'm going to be switching the mood here from the business side to one of those other circles that Jenny had up there, which is the more the academic and research side. And I was just looking over this handout today and was delighted to see that everything's organized around types of clouds, and studying clouds has been my focus for all of those years that Liz just mentioned. And one of the topics that's always kind of bothered me is so-called orographic precipitation. That's been one of the traditional topics in meteorology classes, and I've always felt that it was a bit oversimplified. And as I've worked over the last 20 years or so, let's see. Okay, here we go. Yeah, in fact, I do have this book on clouds, which I wrote back, over 20 years ago, and when I was writing the book, I realized that the one topic that I really had nothing much to talk about was orographic precipitation, or the way the mountains affect precipitation. So I ended up making that one of my research areas for the last 20-some years. And the last chapter of the book is, as you can see, clouds and precipitation is associated with hills and mountains. And whereas the effects of hills and mountains on clouds has long been pretty well understood, the effects on precipitation, not so much. And so that's been my focus. And in this chapter, I start out with this picture that sort of lists all of the different ways that airflow over mountains can affect clouds and precipitation. And let me just go over these sort of one at a time. The first picture there is kind of the classic. The air flows up and over the hill, and on the upstream side, it enhances a cloud, produces cloud and precipitation. If the air is a little bit unstable, that might take the form of convective clouds over the mountain. Another traditional way that's described that mountains affect clouds and precipitation is in the diurnal cycle, where during the daytime, the heating over this elevated region draws air up the mountains and generates convective clouds. And at nighttime, the cooling at the top of the mountains leads to the subsidence. But one of the things I'll mention a little bit later is that this subsidence generates clouds at the base of the mountain during the nighttime, and if the airflow of the moist air toward the mountains at low levels is sufficient, that can actually produced some very strong effects, which I hope I have time to mention later. The next two little pictures show the idea that if you have a pre-existing cloud that's precipitating, goes over a mountain, then on the upwind side, the precipitation is enhanced and it's weakened on the downstream side. The picture on the right is one that was made famous by Bergeron, the so-called cedar feeder effect. So if a pre-existing cloud that's precipitating floats over the top of a mountain, then the air at low levels going up and over the mountain can produce a cloud at lower levels, which the upper level cloud can feed on. As the precipitation comes down into that cloud, it enhances the precipitation. Flow over hills and mountains can also generate gravity waves. The picture on the left indicates sort of trapped waves that you sometimes get, and if the response downstream is strong enough, it can produce a precipitating cloud. The other one, the one on the right, is more to do with a vertically propagating gravity wave, which if it can combine with low-level flow on the downstream side of the mountain, can generate convective clouds, and this is very important in places like the lee of the Rocky Mountains. I'm just going over some of the basic mechanisms here. Another one is if you've got stable air at low levels going toward the mountain, it just gets dammed up against the mountain. It can't rise, and if it's not moving fast enough and it's not unstable, it's not going to be able to get over the mountain. It can just pile up in front of the mountain, and it effectively moves the mountain upstream so that the rising motion is felt upstream in the mountains. This is important in a lot of places around the world. And then the one on the right is if you get the little piece of the picture on the right is a hydraulic jump. If the air comes over the mountain, produces a hydraulic jump like you might see in the flow of rocks in a stream. The hydraulic jump downstream can actually generate convection and be an important process. And finally, this last row is one that I think is especially important and one that we've done a lot of work on. The idea here is that if you have flow over a mountain, it's sort of a dry, stable flow over a mountain, on the downstream side, the subsidence produces a stable layer, and the moist, unstable layer at low levels has trouble producing convection that can get through that stable cap. So the X there indicates moist air coming into the page, and the little clouds can't get through the stable layer. It's produced by the subsidence. Unless that air at low levels encounters a foothill like you see on the right, if the air either toward or along the mountain encounters a foothill, that can trigger the instability, can break through that stable capping layer and produce some of the most intense convection in the world, actually. So all of those things in those pictures are real. These all happen. These are ways that mountains can affect precipitating clouds of various types. But precipitation really doesn't come by these processes alone. The Earth's precipitation comes from really one of three types of storms: convective storms, tropical cyclones, and frontal systems. These are all the three basic types of precipitating clouds. You can attribute essentially all of the precipitation on Earth to these. There's a few places like Hawaii where maybe just the flow over the mountains and the trade winds produces precipitation. But looking at it globally, most of the precipitation comes from these kinds of storms. So if you're going to look, the idea I'm trying to promote is that if you're going to talk about the effect of mountains on precipitation, quote-unquote orographic precipitation, you better be talking about how the flow over and around mountains affects these basic types of precipitating cloud systems. And the rest of the talk is going to be organized around these three types of major precipitation systems and the major ways that flow around mountains can affect them. I'll start with the convective storms, and I'll start with a type that's familiar to us in the U.S. Some of the most extreme and intense convective storms, ones that you hear about producing tornadoes, occur over this region, Texas, Oklahoma, this Great Plains regions. But actually, if this region is not as flat as you might think. To the west is this Mexican plateau, and then the Rocky Mountains extending on to the north. And the flow of moist air off of the Gulf of Mexico comes in at very low levels, and even though it's very unstable, has a lot of moist static energy, it's generally prevented from breaking out into intense convective storms because of the flow off of the Mexican plateau or the Rocky Mountains to the west, and only if the moist air encounters something like a front that can trigger the convection, then it can break through the cap and get these very intense storms. But this type of phenomenon is not just found in this particular part of the world associated with the Rockies and the Mexican plateau, but you see it in other parts of the world. This is a classic example, or a very important example, I should say, over India and Pakistan. And this has an interesting history that it's kind of related to the Symons medal. Sawyer was one of the previous winners of the Symons medal. This is a diagram from his paper. He's a brilliant man. Did many fantastic things, but not much of an artist. But there he has the process pretty much figured out. Even though he had just a couple of extra soundings that were taken basically the year I was born, and he just imagined the whole process fairly accurately. And so we've continued to look at this. We got interested in this because of the TRIM satellite data gives such great coverage over this part of the world, and started pointing out where some of the most intense convection in the world occurred. And it occurs right in this area. And this is from a modeling study that we did in 2010. And the black lines are trajectories of the moist air off the Arabian Sea. It comes in over the desert, it becomes even more energetic because of its passage over the hot desert land. The sensible heat transfer intensifies the potential for convection, but it can't break out because the white lines there are showing the trajectories of the air motion off the Afghan plateau, which are producing a capping inversion, just like we saw in the Texas-Oklahoma example. Here, the triggering almost always occurs when the low-level flow encounters a foothill and breaks through the capping inversion. We also, and this is actually from the TRIM satellite. It shows where the deepest and most intense convection occurs, and it occurs right in that area that I illustrated there. So climatologically, this happens over and over again in this particular area. We see something similar in South America. It's not exactly the same thing, but it's similar. You have a mid-level airflow over the Andes. You get upward motion on the upstream side of the Andes, downward motion on the downstream side, which produces this capping inversion for the flow that's. I don't know if you can, if I can point it out here. This shows the low-level airflow from the Amazon. This moist flow coming down here from the Amazon is channeled along the mountains and is prevented from breaking out into deep convection until it hits this little mountain range down here called the Sierras de Cordoba, or some other foothills of the Andes, and then the orographic lifting of the low-level flow triggers convection. And this, along with that spot in India and Pakistan, hosts the very most intense convective clouds on the planet. And it's all connected with this process that's associated with the flow around the mountains. This, again, the TRIM data showing that climatologically these most intense clouds occur in this area. This is a more global view from the TRIM satellite. And without going into a lot of details here, you can see, hopefully I can get the pointer going here. Here in the summertime in the southern hemisphere, you see this zone next to the Andes. Here in the summertime in the northern hemisphere, this Indian-Pakistan area, and then the area over the U.S. is a little bit out of the range of the TRIM satellite. There's another area here over Africa, but this is more connected with the African easterly waves and is a somewhat different story. Recall I mentioned this diurnal effect, so that in the nighttime you can get this downslope flow off of a mountain range, and if it meets low-level moist flow in a certain way, it can trigger convection. And one of the places where this is manifest very strongly is, again, in India, along the Himalayas. This, don't worry too much about the technical term here. This is just a metric that we use to indicate where the convection has taken on a mesoscale size, and it's become bigger than an individual convective cloud, but it's starting to develop a mesoscale system. And this occurs during the nighttime. This is local time, and this is during the early morning hours. As the flow is coming off of the Himalayas, you get these things breaking out here, and this produces a very complex diurnal cycle. These are just more isolated deep convective clouds. These occur in the afternoon and evening. But if we look at the nighttime, we look at the wider, more mesoscale systems that are bigger, more longer lasting, producing more precipitation. There's a secondary maximum in the pre-dawn hours as a result of that downslope flow. And then as these storms mature, they develop broad stratiform structures that are connected with the mesoscale systems. So that maximizes just a little bit later around sunrise. So you get this very complicated diurnal cycle with some of the more isolated convection maximizing in one part of the day and these mesoscale systems during the early morning hours. Okay, I want to say just a few words about tropical cyclones here, as these are one of our major precipitating systems. And this is a sort of a schematic of typical embedded structure within a tropical cyclone. There's the eye, and then these shadings indicate what a radar might be seeing. So you get this eye wall around this cloud, suppressed cloudy region called the eye, and then often we get a secondary eye wall that forms in the later stage of the storm, eventually replaces the original eye wall. And then there are a variety of rain bands which have a more spiral shape than circular shape, like the eye walls. And you can imagine this is a schematic of what we find that the air motion looks like in a rain band. There's a maximum of wind that follows the axis of the rain band around. This is drawn in the northern hemisphere sense. And then, of course, there's very strong cyclonic flow around the eye. So you can imagine if either one of these features, an eye wall or a rain band, gets lodged up against a mountain, it's going to produce some very strong orographic effects. And some of the worst, most disastrous tropical cyclone events are those that encounter complex terrain. And they've been studied very little, actually. What happens when a tropical cyclone passes over a mountain range is one of the least studied aspects of tropical cyclones. Here's one example of a study by Ron Smith and colleagues where they just show the enhancement of the flow as a rain band became lodged up against a relatively small mountain on a Caribbean island, and the airflow gets into this gravity wave mode, and precipitation is enhanced. In this region here, this is just one example, one of the few studies that's been done. The Taiwanese have probably spent more effort on this than anybody, and this is just a simple kinematic study that shows that if the eye wall of the rain band gets up against a steeper mountain, the enhancement occurs on the upwind side, and if the mountain is not as high, the enhancement is maximized on the downstream side. This is not particularly rocket science, but it's important if you're doing forecasting it gets tricky to know exactly where you're going to get the maximum rainfall and runoff and flooding and everything that goes with it. Maybe another one that I think is pretty interesting is the associated with the eye wall. Now, the eye wall is this big sort of funnel-shaped cloud mass. Air comes in along the ocean surface up in this outward sloping pattern, and then on the interior here of the funnel, you get a strong downward motion that goes along with this whole overturning pattern, and that produces an inversion at the low levels, which is just like the capping layer that we saw on the downstream side of mountains. It's just another way to get this capping inversion. You have very, very unstable or very high energy, high moist static energy air at low levels, but it's trapped beneath this inversion. So this air generally can't rise or do anything. But if the eye passes over a terrain feature like this one, passes over a moderate-sized mountain on the island of Hispaniola, this is actually the eye of the storm. And what happened here? This radar data is showing a tremendous convective response where the lifting of the eye over the terrain feature allowed for this release of that capping inversion to be broken, and the convection could break out in an extreme form. Okay, I want to spend the rest of our time here on something that we're in the process of looking at very actively now, and that is the mountain effects on frontal systems. And but before I get into the scientific side, I have to show you this quote. I think this is just a marvelous quote from Tolkien. The wind began to blow steadily out of the west and pour the water of the distant seas on the dark heads of the hills. I don't think there's anything I could say that could match that language. But Tolkien lived here in the UK, of course. I guess it wasn't called UK then, but he was very aware of these frontal systems coming. I mean, he didn't think of it in these terms, but aware of these frontal systems coming in off of the Atlantic Ocean and passing over the hills. This is something that we see particularly strongly over the Pacific, and in fact, this is a global phenomenon. That was pointed out by Reggie Newell back in 1992, that when you get a trough in the westerlies, somewhere like this, ahead of the trough, this high moist water vapor content of the tropics can get drawn up into the higher latitudes. And associated with the trough, of course, is frontogenesis, the formation of extratropical cyclones and their associated fronts. And what we find on the west coast of North America and South America is that these streamers of moisture, which Newell pointed out are very important for the water balance of the whole Earth, but they're also very important in these west coast regions where we have mountains along the coast, and the frontal systems move in over the west coast of the continents. this part of the picture shows the precipitation associated with this particular storm, and then this is where it's passing over the mountains of Washington State, where I live. And you can see the tremendous enhancement of the precipitation that occurs in that area. First of all, the precipitation is enhanced by the phylogenetic processes along the, ahead of the front. But then when the storm passes over the mountains, things get even more intense. These systems have been called atmospheric rivers by, Newell started that terminology, and it's been picked up by Marty Ralph and his colleagues in the U.S. They've spent a lot of time studying. Ralph's group's been studying these storms moving in off the Pacific for quite a while now, and this is an example from one of their studies that shows the concentration of water vapor and precipitation along the cold front. And what's going on here is that when you've got a strong phylogenetical process, there has to be a low-level jet parallel to the front, and then if it's in one of these situations where moisture is being drawn up from the tropics, this carries a lot of moisture into the higher latitudes, and that gets acted on by the front and then by the mountains. So that's one scale of action. Then as these fronts encounter the mountains, other things can happen. And now you're going to have to switch your brain a little bit. This is the southern hemisphere, so everything may seem a little bit upside down to you. But here are the Andes. The same things happen over in the southern hemisphere. And I particularly like this figure because the circles here show the trajectories of the low-level flow, and the darker lines show the flow just at a somewhat higher level, not really high, but above 1,500. It's below and above 1,500 meters. So you see the low-level flow, when it starts to feel the presence of the Andes, turns sharply cyclonically and goes along the barrier. And so air gets dammed and piled up ahead of the Andes, and the upper level flow moves up and over that. You can see how this effectively moves the barrier forward out over the ocean. So that's one scale of action that can occur. Then, now we'll switch back to the northern hemisphere. This, you think of the low-level flow that's come in and been turned parallel to the mountain barrier. Any mountain barrier is going to have a lot of ridges and river valleys in between them, and that generates a simple gravity wave up and down motion. And this, of course, produces enhancement and I guess disenhancement. Alternatively, on this somewhat smaller scale, while the upper level flow just goes on up, goes over that, and then there's a very strong shear layer between those two levels, and that produces yet a smaller scale of activity, which we've seen in several mountain ranges now. So you can think of the low-level flow down below here, the upper-level flow going up and over it, and then in between here is a very small scale, sort of on the scale of a few kilometers, sort of turbulent up and down motion that you might think is just embedded convection, but actually this occurs in stable situations as well as unstable, and we think we know what's going on, although the reviewers of our paper don't completely agree that we know what we're talking about. But I think this is the smoking gun. I mean, we're pretty sure that these are Kelvin-Helmholtz billows in the shear layer, and this is the radar signature that we get. This is the wind shear derived from the radial velocity observed by the Doppler radar. And you notice it has this kind of complex braided structure here, and this is right in the boundary between that lower and upper flow that I was talking about. And this has another Symons medal connection. Keith Browning and his colleague Chapman produced this paper in 1997. And you can see they observed what were clearly Kelvin-Helmholtz billows that had the same kind of radar signature. And in fact, You can look in the oceanographic literature, you can see this, you can see it in laboratory studies. So we're pretty sure this is what we're looking at. We've seen it in 3 different mountain ranges. We've seen it in the Alps, the Cascades, and the Sierras now. So we're pretty sure. I want to end up talking about the Olympic Mountains. This is a mountain range that I can see out of my office. My office is over here somewhere, and I can look out and see this beautiful mountain range, although I can't really see the contours of the precipitation, which I'm showing here. And you can see, the large values on the upwind side. We have a generally southwesterly flow across the Olympics, and then very little precipitation on the downwind side. So we have very strong enhancement and suppression going on over this region here. You can also see the valley ridge scale superimposed on that. This is a model simulation, but we have detailed rain gauge data that confirm this general climatological structure. And so the latest thing that's about to happen is that this fall and winter we're going to do a field project over the Olympic Mountains starting in November. The field project is really a NASA project to check the measurements from this global precipitation measurement, or GPM satellite, that just went up about a year ago. That's measuring precipitation in higher latitudes as well as low latitudes. It's similar to TRMM, but it's extended into higher latitudes now. This is a nice region because it covers the ocean, the coastal region, the upslope side of the mountains, the high terrain, and then even the downslope side. So we're going to be instrumenting the Olympic Mountains in the following way. We have standard snow measurements at 4 sites here, so-called snowtail, but these are mostly on the lee side. On the windward side, we're setting up a special network of cameras in trees. It sounds crazy, but it's really a great thing, and I'll show you some examples of that. So we have this network of cameras here watching the snow build up. We've got special ground sites all along this Quinault River Valley. This is one of the world's temperate rainforests, right in this region here. And so there's tremendous amounts of rain that occur here, up to, I forgot to mention, but from 2,500 to 5,000 millimeters of rain in this valley here. And these X's are places we're going to have special stations to measure the amount of rain and the drop size distributions and stuff like that. And then there's this other box here is where we have a special high resolution rain gauge network that covers the valley and the 2 ridges on either side. We have 9 radars that we're going to be putting out there. The sort of flagship radar will be the NASA InPol radar. It's an S-band dual polarimetric radar. It'll be situated here on the coast, and it's going to be, we'll have a mobile Doppler on wheels radar here in the valley, looking up and down the valley, so we'll be able to see even underneath the beam of the InPol radar. Environment Canada will have a similar radar here looking at the lee side. And of course, we'll have aircraft. These 3 NASA aircraft will be doing a number of measurements. Just to show you a little bit about what this adventure is going to look like, the InPol radar site is right here. Now, this is a panorama shot, so this is in the southwest and northeast. Northeast, we can see right up to the top of the Olympics, and out to the southwest, we'll see the ocean. So it's a very nice radar site, although it's going to be challenging to clear it off. This is the size of some of the tree stumps. But then this is where the big InPol radar setup is going to be right here. This Doppler on wheels that I mentioned is going to be parked on the shore of Lake Quinault. It's actually going to have its wheels in the back wheels will actually be in the lake up to a few inches, and the radar operators are going to be kayaking over to the radar to run it. Just to show you some of the difficulties, these are some of the more high elevation sites here at this point and this point. This one is only accessed by an old logging road. We're going to bring a trailer up there that's highly instrumented, but to check on it, you guys are going to have to mountain bike or snowshoe in depending on the conditions. And we have an even higher elevation site here where we're going to have to set up a site, and all of the equipment's going to have to go in by pack animals. So this is going to be a very interesting and challenging experiment. This is from one of the cameras. I said it was going to be located in trees to watch the snow. The snowpack develop. These are, you can see, these are graduated stakes here. Turns out the density of the snow is pretty constant, so that we can get the snow water equivalent fairly easily, even though we can't measure directly. This is what it's going to look like as the snow builds up. You can look, this is one day, and then here's another day at the same scene. You can see the snow is piling up there. So anyway, we're going to be putting all of this information together, and so looking at look at these different scales of processes going on in frontal enhancement. So just to summarize, the thing I wanted to emphasize in that chapter in the book and also in the review paper is that if we're going to talk about the effect of mountains on precipitation, it really needs to be done in the context of the storms that are producing precipitation. It's not good enough just to talk about air flowing up and over a hill. It's much more complex than that. You have to first take into account the nature, the dynamics and physics of the basic system that's causing the precipitation, and then look at how the mountains are affecting how it manifests. The convection, the things I talked about here were the capping and triggering associated with the flow over the mountains and the moist flow coming in underneath the capping inversion. The complexity of the diurnal cycles that can arise because of various, especially the nighttime cooling. And on the front, when fronts are approaching the west coasts of continents, especially the two North America and South America, this windward side enhancement has several scales involved. This sort of barrier scale uplift, which may be moved forward of the mountain ranges due to the blocking at low levels, transverse ridge and valley gravity waves, and the smaller scale turbulent enhancement that's kind of our little project. So that's it. That's really all I wanted to say today. I wanted to just take on a traditional topic in meteorology and talk about maybe a new look at it from a very basic standpoint. So anyway, thanks very much. Sure.